Let's jump right into it. Welcome to this explainer. Today we're talking about the absolute unsung heroes of any industrial setup, the valves. In the massive, complex architecture of modern industrial circuits, valves really are the ultimate gatekeepers. They're literally dictating the flow, the pressure, and the overall safety of the entire operation. It's pretty simple. Make the right choice, and you're guaranteeing seamless efficiency. But make the wrong choice? Well, you're essentially guaranteeing a systemic failure down the line. So picture this. You've got a highly pressurized, volatile chemical fluid just surging through an industrial pipeline, and suddenly it hits a valve made from a material that just isn't rated for that specific chemical profile. What happens? We're not talking about some minor, annoying drip here. We're talking about immediate, catastrophic chemical corrosion literally eating right through the metal housing. Or maybe the seals blow out entirely because they couldn't handle the pressure spike. This isn't just about losing some fluid, right? It's about compromised safety, massively expensive downtime, and complete system failure. That's exactly why this matters. And the main takeaway from this explainer today is how to make absolutely sure that never happens in your circuits. Okay, so let's break this down step by step. We're going to cover 1. The material foundation, 2. Pressure and temperature limits, 3. Chemical compatibility, 4. Sealing and mounting configurations, and finally 5. Industry applications. Let's kick things off with Section 1, the material foundation, establishing the baseline. Every solid system starts with the right building blocks, right? And in the world of industrial valves, we basically have 3 main characters to play with. First up, we've got polymer, specifically technical polymer. You can think of this one as your lightweight specialist. It's absolutely perfect for compressed air and simpler, less aggressive tasks. Next is nickel-plated forged brass. This is your reliable standard. It's going to give you the mechanical strength and the long service life you need for a vast majority of universal applications. And finally, we have 316L stainless steel. This is your heavy-duty shield. When the environment is harsh or the fluid is just completely unforgiving, stainless steel is the armor your system needs. Moving on to Section 2, pressure and temperature limits, pushing the boundaries. Now, check out the stark contrast in these pressure capacities. It's pretty wild. If you're running a basic compressed air or water circuit under 10 bar, a polymer valve handles it perfectly, no sweat. But the second you push past that 10 bar mark, polymer is going to fail. You have to escalate to nickel-plated brass, which can comfortably manage up to 40 bar of pressure. But hey, what if 40 bar still isn't enough? For those truly intense, high-pressure industrial applications, 316L stainless steel steps up to the plate, pushing that boundary all the way up to a massive 65 bar. But pressure is really only half the battle here. Temperature is the other piece of the puzzle. Imagine you're operating a system outdoors in a freezing environment. Your standard polymer might only survive down to minus 15 degrees Celsius, but your nickel-plated brass valves, they can keep going all the way down to minus 40 degrees. On the flip side, if you're dealing with extreme heat, standard brass is going to top out around 100 or maybe 130 degrees. For anything hotter, pushing up to 150 degrees Celsius, and sometimes even higher depending on the setup, you absolutely must rely on the thermal resilience of stainless steel. All right, Section 3, chemical compatibility, surviving volatile fluids. So here is an absolutely crucial point. What happens when the fluid itself is the biggest threat to your system? It's a super common trap to just assume a rugged brass valve can handle anything you throw at it. But if your industrial circuit is conveying highly corrosive liquids, you've got to pivot immediately from brass to 316L stainless steel. Stainless steel offers outstanding chemical compatibility, where brass would literally just degrade over time. Trying to use a brass valve for a highly corrosive chemical, that's not a smart cost-saving measure, it's just a structural compromise waiting to blow up in your face. Let's rapidly run through this guide for volatile environments. Because remember, it's not just about the metal body of the valve, it's about the internal seals too. If you're running gaseous oxygen circuits, you need specifically coated clean seals to literally prevent combustion. For high-temperature water and steam circuits, you're going to want to specify EPDM or PTFE seals. And if you're working with synthetic oils, ordinary petrol, or paints and their solvents, a solid brass or steel valve body paired with the right FKM or NBR seal is going to ensure leak-free operation. Which brings us to Section 4, sealing and mounting configurations, securing the system. Take a look at the invisible technology working inside the valve itself. It's pretty brilliant. Many of these high-efficiency valves feature a patented automatic seal wear compensation system. Here's how it works. First, self-lubricating seals engage, and that ensures smooth operation with really low friction. Now, as the valve gets used thousands and thousands of times, natural friction happens, right? But instead of the seal just degrading and eventually leaking, this patented system automatically compensates for that wear. The result? Absolute tightness is maintained over a massive lifespan. It guarantees incredible performance even under a strict vacuum of 755 millimeters of mercury. That is a 99% vacuum. Externally, you also have to think about how you're physically securing the valve to the machinery. On one hand, you have a standard inline setup, which is basically the workhorse of most pneumatic and fluid circuits. But then, consider a high-pressure series configuration that features dedicated fixing screws for through bulkhead or surface panel mounting. What this means is, if you're building a custom machine tool or a really complex control panel, you aren't just leaving the valve hanging loose on the pipeline. You're securely anchoring that forged brass body directly to the panel for maximum stability, even under really severe conditions. And notice the distinct blue lever here. This is super practical. In a massive, complex industrial facility, a technician just doesn't have the time to guess what a specific valve does. So color-coded, repositionable levers allow for really quick visual identification of specific valve configurations and those internal seals we talked about. Plus, these levers can be easily swapped out for butterfly levers or even lockable versions to make sure you have ultimate operational safety during routine maintenance.
All right, last but not least, Section 5, Industry Applications, Tying Theory to Reality.
Let's take everything we've unpacked in this explainer and map it directly to real-world industrial systems. If you're in industries like packaging and textiles, where compressed air and lightweight components are the name of the game, polymer valves are your go-to. Now, if you're operating rigorous vacuum circuits or really heavy pneumatics, the unequaled mechanical strength of nickel-plated brass is for sure your best bet. But if you're working in the food, beverage, or pharma industries, where hygiene, high temperatures, and intense chemical cleaning are just everyday realities, you absolutely need HACCP-improved, fully compliant 316L stainless steel. It all comes down to matching the material to the mission.
Which brings us to our final thought today. I want you to mentally walk through your own industrial circuits right now. You've seen the data. You know the exact thresholds where polymer fails, where brass corrodes, and where stainless steel thrives. So, are you absolutely certain that the valves you've always just considered reliable are actually rated for the specific pressures, temperatures, and volatile fluids they're handling today? Or are they the ticking time bombs of your next major system failure? Take this framework, reevaluate your gatekeepers, and make sure your system's efficiency is never left to chance.